over time, scientists discovered that they needed a better system of measurements. And so the French in the late 1700s developed the metric system. And the first thing that you might think of when you think of the metric system is the meter. It's one of the more common metric units. And so where did it come from? I find this fact interesting. They measured the distance from the North Pole down to the equator, and they cut it up into 10 million parts. And that was the length of the meter. So again, the distance from the North Pole to the equator cut up into 10 million parts. That is the length of a meter. Or at least that's what it was. That's how it became standardized back then. And the fantastic part about the metric system is that once a basic unit is established, such as the meter, every other unit of measurement is obtained by dividing that basic unit into 10 parts or 100 parts or 1,000 parts, or to go bigger, multiplying by 10 or 100 or 1,000. And so if we just draw a line and say this is 1 meter, and then we cut this up into 10 equal pieces. So I'm going to go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Those are pretty good as far as equal pieces. Each one of these is then a new unit of measurement. This would be called a decimeter. So a decimeter is 1/10 of a meter. It's this distance right here. We could then take a decimeter and cut this up into 10 pieces. Those are pretty small. Each one of those is our familiar centimeter. And you can keep going. Cut those up into 10 pieces, you have millimeters, etc. Here's a little chart that talks about these metric prefixes. So if you imagine a meter being right in the middle here, so here's 1 meter, and these are prefixes. If we say deca, that is meaning a decameter, which is 10 of these things, right? And again, a meter is just a little longer than a yard. It's just a little more than like 3 feet, 3 inches, okay? So that's about how long 1 meter is. Again, 10 of those is called a decameter, 100 meters is called a hectometer, and 1,000 is a kilometer, which we've probably also heard of. Again, if we want to go smaller, and again, for you, right, like the length of a decimeter, if you put your hand kind of at an L shape with your thumb sticking straight out, it's about the length from your thumb up to the tip of your index finger, right? That's about the length of a decimeter. A centimeter is one of those cut up into 10 pieces, and a millimeter is one of those cut up into 10 pieces. But again, they're all these numbers that you see here are based on a meter, the standard unit of length in the metric system. Again, for kids, right, you might say it's the measurement of your the width of your fingernail. That's about a centimeter. The distance, again, from your thumb up to your bottom of your thumb up to the top of your index finger is approximately a decimeter. These do have abbreviations as well. So if we wanted to say a kilometer, we would call it a km. A hectometer is hm. A decameter is dam. A meter all by itself is just m. Decimeter would be dm. Centimeter is cm, and millimeter is mm. So we use the prefixes to indicate how many of the base unit of measurements we actually want. It is incredibly important that when you are teaching these things or introducing them to young learners, you are using, again, concrete materials. Handling things, touching things, actually measuring things is what is going to lead into good quality learning. If you have access to a metric ruler of some sort, I would recommend you play around with this a little bit. See if you can measure some things in centimeters or millimeters. This is what a ruler might look like in centimeters. And what you'll notice here is if you investigate from here to here, this is 1 centimeter. But count how many sections this is divided up into. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Remember when we were using our ruler that we use in the English system? Everything was half and fourth and eighth and 16th, not normal numbers that we use in our base 10 system. This is using base 10. And so each one of these is 1 millimeter. Okay. And so again, practice using those things, right? Practice using those things. Now, when you're teaching young learners, it's not necessarily recommended to always just convert between one system and another. It's really good to introduce them independently of each other. But it's also good to know rough estimations between the two. And so probably one of the most common ones that we run into is miles and kilometers. You even notice that on a lot of speedometers on your vehicles, they might show both. Or if you ever drive into Canada, you may see both of those things. And a kilometer is 1,000 meters, like we discussed always. And we might be measuring distances between cities, countries. In space, we might measure it in planets, right? In kilometers in the metric system. But to relate it to miles, a kilometer is approximately, not exactly, approximately 3/5 of a mile. Or inverted, a mile is about 5/3 kilometers. And so we can use that to estimate different distances in both measurements, both units. And so a question for you to think about is this: if a person walks 3 miles per hour, 1 mile every 20 minutes, approximately how many kilometers per hour does the person walk? Take a moment and see if you can just process that and do that conversion. When we talked about doing conversions earlier, I recommended drawing the picture. We have it already up here. And so a person is walking 3 miles per hour. And so we want to know how many kilometers that is. Well, 3 miles would be 3 of these, right? 3 of those. And every mile is 5/3 kilometers. And so if you're going 3 miles, and each mile is 5/3 kilometers, we would multiply by 5/3 kilometers. And that turns into 15/3 or 5 kilometers. So 3 miles is approximately 5 kilometers. Now, if you're a runner, you might have encountered a 5K before. 5K it's a little more than 3 miles. Again, we're approximating. It's about 3.1 miles. But you can see that relationship is pretty close. And a lot of the times, estimating is all we need to do. Here's one more for you to try. If a car is traveling 90 kilometers per hour, what is its speed in miles per hour? I'm going to draw my 2 lines again. Here's 1 mile. Here's 1 kilometer. We know 1 kilometer is equal to 3/5 of a mile, and we know 1 mile is 5/3 of a kilometer. So which one are we going to need in this case? A car is traveling 90 kilometers per hour. 90 kilometers per hour. So what is its speed in miles per hour? So 90 miles is how many, or 90 kilometers is how many miles? That's our question. So we have 90 of these, 90 of these. And so we're going to change it to miles. So we're going to multiply 90 by 3/5 of a mile, because each kilometer is 3/5 of a mile, and we have 90 of those things. When we do that, we get 270 over 5, which is equal to 54 miles, which means we would be going, if we're going 90 kilometers per hour, 54 miles per hour. So here's the greatest thing about the metric system, I think. We've already seen that all of the different units of measurement are based on the number 10. If I scroll back up here to this chart, right? Once we know the base unit of measurement, all we've got to do is multiply or divide by 10 to convert it to another unit, completely unlike the United States system that we currently use. The other great part is that when we talk about volume or mass or weight, it's the exact same prefixes. It doesn't matter if we're measuring something different. These prefixes, which we learn here, are still going to be the same. So when we are measuring volume in the metric system, our base unit of measurement is 1 liter. So the metric unit of volume is the liter. You probably already are all familiar with a 2 liter of soda, right? We've seen those. Cut that in half, there's a liter. That's how big 1 liter is. Now, just like I said, metric units for volume just apply the different prefixes. If our main unit is in the middle there, we put decaliter to mean 10 liters, hecto to mean 100, kilo to mean 1,000, deci to mean 1/10 of a liter, centa to mean 100th, and milli to mean 1,000th. The ones with the stars are the most, the common volumes that are actually used in everyday life. Now, even though these prefixes exist, often they're not used in common, just common talk. So a couple, I guess, questions to try for you. See if you can answer these 3 questions. Funny when I do a copy and paste it, numbers them all as 1, when really that's number 2. So there we go. So 1.3 liters is equal to how many milliliters? So if we have 1.3 liters and we want to know how many milliliters that is, we're going down this way in the chart. And so when we're going down, what we're doing is we're measuring with a smaller unit of measurement. And when you're measuring with a smaller unit of measurement, it means you're going to have more of those things. And so we would have 1.3 liters, and every liter has 1,000 milliliters in it, leading to 1,300 milliliters. So as you go down in your chart, you are going to be multiplying by, again, 1,000, 10, or 100, or something like that, some multiple of 10. 245 milliliters is how many liters? So now we are given, let me erase this. We're given a certain number of milliliters, 245 milliliters. And we want to know how many liters we have. Well, a milliliter is pretty small, and a liter is a lot bigger. And so we are going to have fewer liters than we do milliliters. So 245, as we go up on the chart, we're now going to be dividing. So we'll divide that by 1,000. Every time we go up, it's another power of 10. So this would be 10, this would be 100, this would be dividing by 1,000. That essentially moves our decimal point 3 spots back to the left, which is 245 liters. The last one says 3,487 liters is how many kiloliters. So 3, 4, 8, 7 of these. We are going up to a bigger unit of measurement, so we'll have fewer of them. And because it's 3 spots up, I'm going to take 3, 4, 8, 7, divide it by, again, 1,000. It'll move my decimal 3 spots back to be 3.487 kiloliters. And so that's our metric units of volume. Now, another thing that's important to know about the metric unit of volume is sometimes what we do is we will measure, like we mentioned earlier, in cubic measurements. And so what you see here is actually a picture of 1 liter. We just talked about one of those things. But if we measure a cube, oh, that's not what I wanted to do. I'm going to draw a cube, a better cube than that. Let's try again. So if I measure a cube, or I draw a cube, and that cube on each side is 1 centimeter. 1 centimeter and 1 centimeter. It's going to be a pretty small cube. You can imagine, you can just sort of pinch it right between your fingers. Imagine a little cube there. That is 1 cubic centimeter. We talked about cubic inches in the previous video. We use that to measure 1 milliliter. And so what you'll notice here is that a metric unit of distance, when you cube it, is connected to a metric unit of volume. A cubic centimeter is equal to a cubic milliliter. The same thing over here, a cubic decimeter. Remember, put your hand out, measure from your base of your thumb up to your tip of your index finger. That's about a decimeter. Imagine a cube that big. Boom, boom, boom. Right there's your cube. That's how big 1 liter is. So I think that's pretty cool that the metric units of length are also connected to the metric units of volume. That is not true in the US English system. A foot and a quart have nothing to do with each other. An inch and a gallon, completely unrelated, but they do connect with each other in the metric system. And so finally, let's talk about the metric unit of mass. Now, mass and weight are connected, but they do measure slightly different things. Mass in the metric system the difference is gravity, right? Mass talks about the amount of matter that makes up an object. Write that down. Mass is the amount of matter that makes up an object. Weight is how that's connected to gravity. So, right, if you go to sea level and if you go to the top of a mountain, you will weigh a slightly different amount because of pressure. Same thing, right, if you go to the moon, your body mass hasn't changed, but you'll be slightly weightless. You'll weigh a lot less, but your mass doesn't change. So they are connected. And so we, in the metric system, measure mass really instead of weight. And so the gram, if we're thinking about the same little chart that we've looked at before, the gram is that central unit of measure in the metric system. the gram. And again, like before, we have different prefixes, deca, hecto, kilo, deci, centi, milli. They mean the same thing. Most frequently, we use the kilogram a lot. We use gram a lot, and we use milligram a lot. Those are very common units of mass. And so, just for the sake of being able to compare and put this into perspective with measurements that we know, we measure our weight in pounds, right? We measure how heavy things are in pounds. A kilogram, 1 kilogram, is approximately 2.2 pounds. So 1,000 grams, kilogram is 1,000 grams. And if we want to put it into our English system, it's approximately 2.2 pounds. So just again, if you want to measure or do a little practice with some conversions, let's look at this. Could you measure your own mass in kilograms? How about the mass of a 10-pound bag of potatoes? How about the mass of 1 pound of hamburger? So restating these things in kilograms. Now, right, you're all going to have your own individual mass, but we'll do the 10-pound bag of potatoes. So again, if we think about a drawing where this is 1 kilogram, and we know that it's 2.2 pounds, I'll abbreviate LB, and then we're going to measure 10 pounds of potatoes. Well, this is 2.2 pounds, and I want 10 pounds. I want to see how many of these are going to fit into 10 pounds. And so how do we do that? We will be dividing. We'll be dividing our 10 pounds by 2.2, and that is going to give us approximately 4.55, approximately 4.55 kilograms. The mass of 1 pound of hamburger, same thing. So if we just do a little sketch, the sketches help. This is 1 kilogram, which again is 2.2 pounds. And we want to know how many kilograms 1 pound is. Well, 1 pound is actually only a part of this, right? It's going to be only about that much of this section. So we're going to take our 1 pound and we're going to divide it by 2.2. And we will see that that is approximately 0.45 kilograms. So to wrap this up, we'll talk about temperature. In the English system or imperial system, we learned about Fahrenheit. And in the metric system, commonly we use Celsius. And Celsius, you can guess, because the metric system is all based on powers of 10, water freezes at a nice convenient 0 degrees, and it boils at 100 degrees. And these are on the Celsius scale. So Celsius scale. It originally was called centigrade, centi meaning 100 grades, but it came to be called the Celsius scale over time. Now, there is another scale in the metric system, and it is called Kelvin. That may be one that you are unfamiliar with. And heat, if we go briefly into the idea of physics, heat is related to the motion of molecules. So the faster molecules are moving around, the greater their heat is. And at negative 273.15 degrees Celsius, something very important happens. All molecular movement ceases. It stops. This is called absolute zero. you essentially cannot have anything colder than that. Because again, once all molecular movement stop, it can't stop more than being stopped. And so this was discovered by British mathematician and physicist William Thomson, who was known as Lord Kelvin. And so this is, there's something called the Kelvin scale. And the Kelvin scale says that 273.15 degrees on the Kelvin scale is 0 degrees Celsius. So essentially, 0 degrees Kelvin is where all that molecular movement stops. You don't really need to know too much about this. I just wanted you to be aware of it. And know that in everyday use, Celsius is the standard temperature measurement, but in science, Kelvin is often the standard unit of temperature there. And so to wrap this all up, eventually the metric system led to what's called the International System of Units. It's sort of a modern version of the metric system. Again, it was established by international agreement. And there are really specific definitions now established by this international system. For instance, a second of time is measured by, it's interesting, the time required for a wave of the cesium-133 atom to complete 9,192,631,770 cycles. I know, you don't need to know that, but we've standardized things so much that there's none of that, I guess, wishy-washy measurement like there used to be with hands and stones and things that were not constant. All our measurements are incredibly accurate today.